Hi, everyone, and welcome to our talk today about adding custom Gateway API extensions to Envoy Gateway. My name is Daich. I'm a development architect at SAP and a maintainer in the Envoy Gateway project.
I'm Teju Nareddy. I'm a senior software engineer on the traffic team at Confluent. Yeah, so today's talk is on extensibility in Envoy Gateway. Both of us are here today because extensibility is what makes or breaks an open source project. So let me give you a quick example from my work at Confluent. On the traffic team, we are end users. We run Envoy at scale in production. We've been running Envoy proxy for 4 years, and starting this year, we actually run Envoy Gateway in production as well. So we've always had a in-house built custom XDS server, and this year we have successfully migrated a portion of our workload to Envoy Gateway. Now, this initial decision to adopt Envoy Gateway wasn't an easy one. And that's because our main top of mind concern was around extensibility. So yeah, adopting an open source XDS server, we were kind of worried if we were giving up control to support our own custom policies, or if we'd be forced to maintain a fork of Envoy Gateway in the future to support our legacy XDS configurations. But when we investigated Envoy Gateway and did a deep dive with maintainers like Guy, we actually found Envoy Gateway was built from the ground up for extensibility. So today, Guy and I will talk about a specific feature in Envoy Gateway called Extension Server. In my opinion, this is one of the most powerful extensibility features that Envoy Gateway has, and it is essentially what made Confluent's adoption of Envoy Gateway possible. So with that, I'll hand it off to Guy.
Fantastic. So today we'll give a bit of background about Gateway API and Envoy Gateway, and then dive into the extension server topic, discussing motivation, use cases, and some of the main concepts there. And we will close with a demo showing how you can define your own custom extensions and then implement them with an extension server. So starting with Gateway API, Gateway API is a working group in Kubernetes that is defining the next generation for ingress APIs in Kubernetes clusters. It's a very comprehensive API that has a lot of functionality out of the box. It's also a very modular API that is composed of many smaller resources that can be owned and operated by different personas in a shared and multi-tenant environment. And while it is very comprehensive and provides a lot of functionality out of the box, it's also very extensible. Gateway API has several extension points that are already part of the API itself, allowing users and implementations to extend Gateway API beyond what's currently supported in the API itself. Envoy Gateway is first and foremost an implementation of Gateway API. So that means that Envoy Gateway translates Gateway API resources into XDS. It uses Envoy as its data plane. However, Envoy Gateway also adds many more features on top of what is currently supported in Gateway API using those previously mentioned extension points. So for example, in Envoy Gateway, you can implement a regex rewrite using a custom route filter. You can route to a Unix domain socket endpoint using a custom backend resource. And Envoy Gateway also offers a variety of policies spanning topics like security, management of client and backend traffic, and even data plane extensibility. So allowing you to add features like jot validation, tuning protocol parameters, configuring load balancing policies, and even adding your own extension filters like WASM filters. But the topic of our conversation today is actually the topic of control plane extensibility. So we're going to be discussing the extension server feature in Envoy Gateway that makes it possible for end users to implement their own extensions, define their own extension resources that comply with the Gateway API extensibility points, and then enhance the Envoy Gateway translation engine to actually implement those extensions by making the necessary XDS configuration changes. So we've seen a couple of use cases for the extension server in the community. First, from time to time, there are certain features that just go beyond the scope of the Envoy Gateway project and cannot be accepted into the open source. This happens because a feature perhaps does not have sufficient community support, or it creates a certain security issue, or just contradicts with gateway API definitions. These are some of the common reasons why we as maintainers see certain features not being accepted. And then those users from time to time would choose to use the extension server in order to tailor Envoy Gateway to their needs. However, we also see the extension server being used in a more tactical fashion. So, for example, some users and organizations would contribute certain features to the open source, but in order to be able to gain access to these features and capabilities faster, they would also in parallel implement that feature using an extension server and then eventually converge with the open source once their contributions were accepted, merged, released, and adopted. And finally, we've also identified several large-scale extension projects that use Envoy Gateway as a foundation, but have to extend it significantly. So, for example, the Envoy AI Gateway project that was mentioned here previously has a very comprehensive AI-oriented API. And in order to implement that API, that project leverages the Envoy Gateway extension server. But besides open source projects, we've also seen some vendors use the extension server. So typically, vendors that provide their own custom distributions of Envoy Gateway may want to offer users certain differentiating capabilities and custom features that are not part of open source Envoy. And then the extension server can be used to enable such features, which are shipped with these custom distributions. Now, when faced with the need to extend a project, and specifically the Envoy Gateway project, there are a couple of options. So you can always fork, but that is highly unrecommended due to the maintenance costs associated with such a path. And Envoy Gateway actually offers several options for extensibility. The first one being applying XDS patches using the Envoy patch policy. This is a very good option for simpler use cases, where you don't have to have significant logic, state management, and such. However, when you are faced with a significant extension story where you have to manage state, where you need context to apply your extensions, where you actually want to be able to write code to implement these mutations that you need, we would recommend evaluating the extension server as a more powerful tool that supports these sorts of use cases. So finally, what are some of the main extension server concepts? First and foremost, we have the service itself. It is a gRPC server that implements an interface defined by Envoy Gateway. The communication with the service can occur over TCP or Unix sockets, and you can use TLS or MTLS if needed. And the service itself can actually be deployed everywhere or anywhere. It can be a sidecar, it could be a separate deployment, can be out of cluster. And as part of the configuration of Envoy Gateway, you will provide the address of the extension server. Now, the interface is essentially a collection of hooks for mutation of various XDS resources. So, for example, there are hooks for XDS routes, for virtual hosts, for listeners, for clusters, secrets, and so on. So when an extension server registers to a specific hook, Envoy Gateway will invoke that extension server and provide to it the XDS resources that Envoy Gateway translated from Gateway API. And then the extension server has the option to mutate these resources before they are being used to actually program the proxy. However, typically that is not sufficient, having this external global mutation engine to implement more advanced use cases. For example, let's say that we want to implement a buffering feature in Envoy Gateway. It's totally reasonable that we'll want this buffering feature to apply to just a subset of the resources. And maybe we want to have different buffer sizes for different resources. So in order for us to be able to apply such contextual mutations, this is where the concept of extension server resources comes into play. These resources are essentially Kubernetes CRDs defined by the extension developer. Envoy Gateway is configured to watch these CRDs, and when Envoy Gateway invokes an extension server hook and passes along an XDS resource that is translated from a Gateway API resource that is attached to an extension resource, that extension resource is provided as context. So for example, here you can see in the slide that I've created an example of a custom buffering policy, and I've attached it to a specific Gateway API gateway. And so when an extension server would be invoked with an Envoy listener generated for this Gateway API gateway, the hook would also provide the buffering policy as context, allowing the extension server developer to actually apply the necessary mutation and configure it accordingly. So There are three major extension server resources that we have in the model. First, we have policies. Policies attach in Envoy Gateway right now to gateways. They have a target reference section that defines the scope of their attachment, and they can be used as context for HTTP listener hooks and the post-translation hook. So the buffering policy that I presented in a previous slide is an example of that. But we can also apply route level extensions using custom route filters. In Gateway API, route filters are typically used to change traffic as it goes through the proxy, for example, rewriting URLs, but it's also possible to reference a custom extension ref filter that you as an extension developer can use to implement whatever route-specific feature you need. So for example, you can use this to implement request hedging for specific routes, which is currently unsupported in Envoy Gateway. And finally, the last extension resource that is currently supported is the backend resource. So in Gateway API, we have backend refs, which is a list of backends, typically Kubernetes services, but actually these can be any resource. And when you are implementing a custom extension backend, you can add your extension backend to those backend refs, and then Envoy Gateway would translate these backend refs into a Kubernetes cluster, an Envoy cluster, and this extension backend resource would be provided as context in the cluster mutation hook. So for example, we've seen users use this to change clusters from being regular clusters to original destination clusters, allowing an external load balancing algorithm to select the target endpoint, for example, in AI use cases. So I think that pretty much sums up this part of the talk, and we can move on to the demo.
Okay, awesome. Okay, yeah, so for the rest of the session, we'll do a demo with extension server. So we're going to follow through a real-world example scenario, and we're going to configure our own extension server with our own XJS mutations. The goal here is to provide you all with a guide in case you ever need to extend Envoy Gateway yourself. So for the demo scenario, we're going to integrate Envoy with Spiffy and Spire Agent to perform service-to-service authentication with backends. This scenario is not natively supported by Envoy Gateway out of the box, so that's why we're going to write our own extension server. Let's understand the scenario requirements first. We're essentially going to configure Envoy to retrieve a TLS client certificate, specifically an SVID, from Spire Agent. Let's assume Spire Agent is running on the same host as Envoy, and it exposes a secret discovery service API over Unix domain socket. And then we'll configure Envoy to present that certificate in any connections to backend. So Envoy will essentially perform MTLS with backends. For the demo, we're going to start the demo in this sandbox architecture, and we're going to work our way up to support the scenario we want. So this sandbox is actually taken directly from Envoy Gateway documentation. I deployed it to my Kubernetes cluster in a minute. In this architecture, we have Envoy Gateway in the control plane. It's watching Kubernetes Gateway API resources and other Kubernetes CR, and then programming Envoy to perform TLS with the backend. So here we have Echo server, dummy Echo server, and we're only doing TLS. There is no MTLS and no client certs. We are going to transition this to this architecture. So essentially, we're going to write our own extension server and deploy it so that extension server will take the XJS from the previous slide and mutate it to configure Envoy to watch Spire Agent and send the SVID to Echo server. For completeness, we're also going to implement our own policy. So on the top left, we're going to make this custom backend MTLS policy. The goal here is when the cluster operator adds that policy, then we're going to turn on our mutations. Otherwise, we're going to no-op our extension server and revert to the previous slide's architecture. Now, before we dive into the demo, let's understand the actual mutations. They're actually fairly straightforward. They're both on the cluster config. The first mutation we're going to code is if the policy exists, then we're going to add in this hard-coded cluster for Spire agent. So we're just hard-coding in the Spire agent UDS path. Next mutation is we're going to iterate over all other backend clusters. And for each cluster, we're going to mutate the upstream TLS transport socket. So here we're adding in SDS seeker config, and we're essentially telling Envoy to fetch the specific cert with the spiffy ID from Spire agent. And here the spiffy ID represents the Envoy proxy. So with that, let's go to the demo. We're going to first start by implementing the custom policy. Then we're going to configure Envoy Gateway to watch that policy and call the hooks on our extension server. And then we're going to actually implement our extension server, deploy it, and verify things work end to end. So give me 1 second. Okay, so this demo is not live, it's pre-recorded. Okay, I have my ID here. So like I said, we're first going to start with the policy. So this part is all standard Kubernetes. I'm using KubeBuilder controller gen to define our policy. You can see I've defined my spec in Golang. So this spec has 3 fields. The first field is our standard gateway API target refs. So this is the gateway that we're targeting with the policy. These next 2 fields are my own custom fields I defined. These represent the spiffy trust domain and workload identifier. And we're going to use these fields in extension server in the future to form the spiffy ID. So now we can use controller gen to generate this CRD manifest and apply the CRD to our cluster. And then I'll also show an example of the actual CR on that CRD. So this is an example of what a cluster operator would configure to turn on our mutation. So here they're targeting the single gateway in the cluster named AG, and then they've configured this example trust domain and sample workload identifier for Envoy. So we can go ahead and apply these to our Kubernetes cluster. And now we're going to do the second part, which is configuring Envoy Gateway to watch that policy and then call the correct hooks on extension server. So yeah, this part is all configured through another CR called Envoy Gateway. So this is a CR that Envoy Gateway ships with, and we place it in this config map. When Envoy Gateway starts up, it essentially looks for configuration and startup options in this CR. For today, we're going to focus on this extension manager subsystem on line 14. So this subsystem basically has all the configuration for how Envoy watches policies and interacts with extension server. So here on line 17 to 20, I've configured Envoy to watch the sample, the policy that we created. And then here I'm telling Envoy Gateway which hooks to call on our extension server. And of course, the service discovery for extension server. So there's a lot more options we can add here, such as fail open, fail close, TLS with extension server, but we're keeping it simple for the demo today. So with this, we'll go ahead and apply this to our Kubernetes cluster as well. And now the pipeline will actually be broken right now because we haven't deployed Envoy Gateway, we haven't deployed extension server, but we will go ahead and now implement the mutations and deploy it. So, like Guy said, extension server is just a gRPC binary. It can be in any language. You can deploy it however you want. For this demo, we wrote it in Golang. So here's our example extension server. You can see the main function has a few CLI parameters. And the main business logic is actually down here on line 99. So here we're registering our gRPC service. Looking in this package, we can see we pull in this unimplemented Envoy Gateway extension server RPC definition. These are the RPCs that extension server provides. And here we're just returning an unimplemented status code for each RPC. Now, in the same package, we're going to go ahead and actually implement one of these RPCs. So in this file, we've overridden the post-translate modify hook. When we look at the RPC definition, we can see Envoy Gateway calls us with this request message. So this request message has all the resources that Envoy Gateway knows about, or all the XDS. And it also has the context. As Guy said, this context is where we'll have our custom policy that we just defined. So the first thing I'm doing on line 86 here is essentially iterating over those context resources and parsing out the custom backend MTLS policy that we defined. There's a lot of parsing logic that's hidden, but this code is available on GitHub. If the policy doesn't exist, we're just no-opping and returning all the resources as we receive them. If it does exist, then we're going to do our 2 mutations. So as a reminder, the 2 mutations are to 1, add the Spire agent cluster, and 2, mutate all other clusters to have the SDS configs. So now we'll go look at the code for that. It's actually fairly straightforward. First mutation is on this line right here. We're just appending this hard-coded cluster, and you can see this has the hard-coded path for Spire agent. Second mutation, we're iterating over all clusters. We're checking if a cluster is associated with a HTTP route. And if it is, we are looking for the TLS transport socket. If we find one, we unmarshal the transport socket. And then we go ahead and we add on that TLS certificate SDS secret config on line 175. So here, the SDS config source is hard-coded to Spire agent cluster, and then the SPIFFE ID is actually derived from the policy. So you can see here, we're taking the trust domain and the workload identifier that the cluster operator configured and forming our SPIFFE ID. And that SPIFFE ID represents the Envoy proxy. So with that, that's our whole extension server. And I've already gone ahead and deployed the extension server to our Kubernetes cluster. We can go look at the pods in the namespace. So here we have the fake Spire agent, we have extension server that was just deployed, and then we have Envoy Gateway as well as Envoy proxy itself. Now, if you took a look in that Golang binary, I added some log lines in extension server. So we can go look at the logs of this pod and make sure it's actually doing something. We've already added all the other features or the policy and configured Envoy Gateway, so it should be working. We can see the hook was invoked. We can see we successfully added the Spire agent XDS cluster, and we mutated this specific cluster that is associated with the dummy echo service to have SDS config. To double check things are working, we can look at the Envoy config dump. So I have the Envoy admin port open here, and looking at the config dump, here's the cluster config for the dummy echo backend cluster. So yeah, we can see here in the TLS transport socket, we added in the SPIFFE ID as well as the SDS config source. And then of course we have the hard-coded Spire agent cluster name. And then finally, we can verify things work end-to-end. So here I'm going to emulate the curl client on the left, send a request through Envoy to the echo server. The echo server should echo back details on the connection it received. And when I send this request, we can see that echo server not only received a TLS request, but it also received a peer certificate. So this means that echo server received SVID from Envoy. And yeah, that is the end of our demo. So yeah, thanks all for coming. We have some resources available. So Guy linked a bunch of open source documentation on extension server. I've linked a GitHub PR that has all the code that we used in this demo. And then tomorrow at KubeCon, Isaac is going to be talking about his journey with Envoy Gateway. So if you're here, please attend that talk. Thank you all, and I think we have time for Q&A.
Do we have time for questions?
Do we have time for questions? I think so. We have 2 mics. Yeah.
Hello. Hi. I was wondering how welcoming you would say the extension is to new contributors as open source contributors.
You mean to say Envoy Gateway?
Well, the extension server portion.
So I think that we've done our best to improve documentation around that feature and how it works. I mean, it's definitely a bit complicated because it's a couple of level of abstractions, right? Because it's essentially using Envoy Gateway as a way to implement a custom extension. We are hopeful that this talk, as well as some of the improved documentation, would make it easier for people to actually go ahead and implement it. Overall, as Teju has shown, you can use pretty standard tools like KubeBuilder and gRPC to build out these servers. So we've done our best to use pretty common technologies that should make it pretty simple for people to implement these extensions. Of course, you would need to have some Envoy knowledge, right? I mean, essentially, you are touching XDS resources, changing them, adding them, and so on. So you need to have a pretty good grasp on Envoy. I think that would be like the most significant barrier of entry, probably, into that feature.
Thank you.
Welcome.
Hi. Yeah, thanks for the talk. So in addition to the extending the standard resource or implementing the extensions for the standard extension points, is there also any work on the Envoy Gateway front to actually make things like config provider or the infra provider be actually pluggable without having to fork?
That is a great question. So I think that, I mean, we've definitely seen like over the last year, significant evolution of the local configuration provider. So I mean, the concept of a provider being a generic mechanism, right? I mean, we initially started with just using Kubernetes resources coming from an API server, and now Envoy Gateway also supports really in a very mature way using resources from the local file system. So we've definitely added, I mean, we've taken this from like a generic concept into another example of showing that you can really implement a custom provider. But right now, to the best of my knowledge, there is no extensibility to that level that you're referring to, right? So, I mean, if you want to build your custom provider, basically a different source of the configuration, I think that right now the only option is to fork. But I mean, if there are other use cases, I mean, do you have like a specific use case in mind, just out of curiosity, like console or?
I mean, can I use it? Yeah, we actually have a need for using a custom infra provider. So instead of actually provisioning directly using the Kubernetes APIs, we actually use a different service to do the provisioning of the actual data plane. And same thing on the config side, we don't actually read directly from the Kubernetes APIs, but there's some other intermediate services in play. And
I see.
So yeah, we currently have to actually fork it for that reason, but we would prefer not to. So if we could avoid that, yeah.
Yeah. So I think that we should definitely look into supporting common use cases. For example, getting a configuration from an RDBMS, right? I mean, that could be a very generic feature that could be part of the open source. But if you really have your own custom APIs, then yeah, we need to either solve that with extensibility, or right now there's a fork as the only path to achieve that.
Yeah, I was mostly wondering if there was a way for using things like Golang plugins or some sort of where you can actually drop in a module for a the Envoy Gateway already has the interfaces for things like provider, infra provider, but it doesn't have a way to for us to drop like a binary module.
Yeah, to dynamically inject an implementation. That's a very interesting idea. I mean, I've never heard it come up before, but definitely an interesting one. Please, open an issue, and I think that would be definitely an interesting issue to discuss with the community, for sure.
Thank you.
Just got a question to better understand the demo. I haven't used Piffy before, so I think I don't want to start a conversation on why I would use Spiffy versus like MTLS with Linkerd or IST or like a service mesh, but trying to understand from the demo, I was curious because when you configure an Envoy Gateway, you have an option to specify, you could do TLS termination there, and you could specify your TLS hostname or mount a secret there. And then it'll look at the secret in the namespace and be like, hey, this is what we're going to use. Is the problem you were trying to solve is the trust for all the services that wanted to do MTLS? Is this what would have made sure that whatever TLS certificates or MTLS you wanted to use with Spiffy is already baked in, so there is trust before, and you don't have to like customize your nodes or pods to say, well, this is the custom trust you have. Does that make sense?
Yeah, so let me give some background. So Envoy Gateway does support configuring MTLS out of the box. So you can tell Envoy Gateway, like Envoy should use the certificate and present it to backends for MTLS. The issue is that in standard Envoy Gateway, it looks for that secret in Kubernetes secrets. So the whole idea with Spiffy and Spire Agent is to have something on the host, not in Kubernetes API server, that exposes STS API just to workloads on the host itself. So that's why we can extend Envoy Gateway to support this, but we decided to do this in extension server. So yeah, does that answer your question?
Yeah, I think so. I think so because recently I was configuring something with, we were trying to solve a problem where we weren't using MTLS, but we kind of do. We didn't want to just roll out service mesh for a particular use case, but we wanted to we wanted to have that kind of service-to-service communication and also roll out HTTPS too. So there were a lot of things we wanted to accomplish, and the way we did that is actually using core DNS and local DNS to point to the internal route of Envoy and deploying an internal Kubernetes-only gateway where we had a self-signed cert or like using Let's Encrypt or something, right? And then mount it to Envoy. So I was just curious how this kind of goes in well with that, but I get what you mean now because what if the secret is not available within the cluster and you need it? Yeah, I think that makes sense. Thanks for
take
answering.
a look at Spire Agent and Spiffy, and that'll probably help too.
Sounds good. Thank you.
Yep. Yeah, I think we're out of time. Thank you all.
Thank you, everyone.